Hello everyone. This is continuation of our last lecture on electrostatics where we discussed about what electric field is, what are electric field lines, what is electric flux and what is an electric dipole. And we calculated the electric field due to a dipole along its axial line, and I had given a task to calculate for equatorial line. So let's start with that. So field due to dipole in equatorial along equatorial line. Okay, so this is our topic. So dipole is nothing but equal and opposite nature of charges separated by some distance, right? So let's say this is minus q, this is plus q, and this is a dipole, right? This system is a dipole. This is separated by distance, let's say 2a, and along the equatorial line at a distance r from midpoint at point p, what is the electric field? So the aim is to calculate what is the electric field at p, right? So let's call these points are a and b. So you know that at point p electric field will be because of these two charges, right? So as we already studied, the direction of electric field is away from positive charge and towards the negative charge. So because of this positive charge p plus q, the direction of field will be in this particular direction, right? Let's call this as EPB, something like EPB, right? That field on P due to B, right? And this A being a negative charge, the direction of field will be towards itself. So let's call this particular field direction is as EAB. And let's say this angle is theta, right? So this is again theta, right? So now you can see that there are two fields acting here, right? One is EAB, one is EPB. And we need to calculate the resultant field, which should be something in this direction, which you can say using the vector law, right? So let's say now, so you can see that one component of this field will always cancel, right? So this is what 90 minus theta, right? So this component for EAB will be what? EAB sine theta. Again, this will be also 90 minus theta since it is a vertically opposite. So this component will be what? EPB sine theta, right? Let me call this as EPA, not EAB. So this vertical components will cancel out each other. So the component of interest is the horizontal component. So one would be EPB cos theta and another would be EPA cos theta, right? Okay. So this is along, if you see the direction, this is along, if I take it as XY axis, the field is along the negative X axis, right? Negative X axis. So net field is what? EP, let's say it is what? EPA cos theta plus EPB cos theta, right? So it's nothing but EPA plus EPB cos theta, right? Now we know the formula for electric field. So EPA is nothing but KQ by this distance squared. So this distance is what? Since this is A, this is A, this is R. So this is what? Under root A square plus R square, right? So this will be KQ by A square plus R square since it is under root whole square. So this is, which is same as the magnitude of EPA is, which is same as EPB, right? So net electric field EP, and also the cos theta. Cos theta is what? Cos theta is A by under root A square plus R square. So net field EP is what? 2 EPA cos theta, because since both magnitude are same. So it will be what? 2 KQ by A square plus R square into A by under root A square plus R square, right? Okay. So let me rearrange it. It will be KQ 2A upon A square plus R square power 3 by 2, right? So this is what it is. So now we have the same assumption that the position where we are calculating the field is very higher than the distance between the dipoles, right? Or half of the distance. So a square plus r square will be approximately equal to what? R square, right? Since a is very small and it won't have its contribution, enough contribution, right? So now ep will be what? Kq 2a upon r square power 3 by 2, right? So it is kq2a by r cube. So q into 2 is what? Dipole moment, charge into distance between them. So kp by r cube. So this is the expression for electric field, kp by r cube, due to dipole along its equatorial position, right? Okay, so let's get back to axial and let's compare both of them. So dipole, field due to dipole along axial and along equatorial, right? So along axial we calculated the field was given by 2 kp by r cube, right? Along equatorial the field was given by kp by r cube, right? Let's call this as ea and this call this the e. Okay, so this is the field due to dipole along the axial line, this is the field due to dipole along the equatorial line. So ratio if I take, so axial by equatorial, this will be what? 2 kp by r cube upon kp by r cube, which is what? 2 by 1, which is equal to 2 is to 1. So field along the axial line is 2 times stronger than the field along equatorial line, right? But you can notice one thing, that the field of due to dipole, if be it axial equatorial, it is inversely proportional to the cube of distance where we are calculating the field, right? This is a point to remember, because in normal for static charges, for point charges, we saw that field was inversely proportional to square of distance, which was the inverse square law. Okay, so this is a point to note for dipole. So yeah, so we will be closing dipole here. And if I talk about the physical significance of dipole, I have already discussed, like the, let's say, some molecules in chemistry. So there are two types of molecules, right? One are neutral molecules, which has no polarity, right? So let's say CO2 molecule, right? So this is a neutral molecule, right? Because even oxygen has more electronegativity, but because it is effect in the both direction, the net dipole moment will be zero, and this is a non-polar molecule, right? But yeah, if I apply an external electric field over here, then we can make this polar, but that is a difference. But let's talk about a water molecule. This is a water molecule, right? You know, water is a sp3 hybridization. It has it has two lone pairs as well, and this bond angle is 104.5. So here you can see oxygen is more electronegative and hydrogen is less electronegative. So as I said, dipole moment direction is from negative to positive. So there exists a dipole P, right? And this is again a one pair of dipole, which is OH pair. So this is P. So this is a polar molecule, right? This is a polar molecule. So the nature of molecule, right, it actually depends on its polarity, whether the molecule is polar or not. Because you will see, you'll study the concepts of hydrogen bond, on how polarity makes the strongness of bonds. Like what in water, you will see that water has an intermolecular hydrogen bond, so its boiling point increases, it becomes less volatile and things like that. So, and even solubility, like we say that like dissolves like, so polar solutes are dissolved in polar solvents and something like that. So this concept of dipole is physically, you can see in your molecule concepts as well. Okay, so yeah, let's, right, so we just studied about the electric field due to a dipole and in its equatorial and axial positions, and what is the significance of a dipole, why we were studying a dipole. Okay, so let's talk about now what happens when dipole is itself is a placed in external field, and what happens on it, right? Okay, so as of now we will consider the field as uniform. So uniform field is what? Let me talk about a bit brief about uniform electric field, right? Uniform electric field, right? So I said that as we move away from a point charge, or So the intensity of field will go down, right? The magnitude of strength of electric field density will go down, right? Uniform electric field is nothing but this is an assumption, right? Let's say we have some very big charge at some point, right? So it will emit electric field along all directions, right? The field will be varying, right? If you see point by point, the field will be varying. But since because of the magnitude of charge, if I take one particular instance, I would say that the magnitude of electric field at this particular area or at this particular line is constant, right? So it's like let's say there is a big circle, right? There is a very big circle of infinite radius, but somewhere if I take a small point of it, it would look like a straight line, right? So uniform electric field is something similar to that. So let's say this is a minus q and plus q, right? So I said that electric field lines will be something like this, right? It will be like this. It will be like this, right? But if these magnitudes of these charges are very high, so you'll see a lot of lines from here, right? But if you take one part of it, right? One part of it, only one part of it, you would see that the field magnitude is approximately same in this particular section, right? So this is uniform electric field, right? Where we assume that the field is almost constant and it is represented by the this straight field lines, right? This is uniform electric field. Okay, so the topic is torque on a dipole placed in uniform field, right? So let me draw a diagram first. So let's say this is a region which has a field E, right? This is emitting electric field E in all directions. Okay, this is the reason. And I have placed a dipole here. So this the dipole will look like this: minus q plus q, right? And let's say this field is making some angle theta with the dipole, right? Okay. So we are talking about torque on a dipole which is placed in a uniform electric field. So this is the representation of uniform field. If we assume that in this region the field is uniform, right? At every point, if you see a point at a same level, the electric field will be same, right? So we need to, the topic is torque on a dipole. So what exactly is torque? So in last class, rotational mechanics, you would have studied a term called torque, right? So like it is the rotational counterpart of force, right? It is responsible to rotate any particular object. You would have seen, you would have done some experiments maybe to understand what exactly is torque. So it is the rotational analog of force, right? So let's say this is a board, right? So if I put a force from this point, right, and let's say there is no wall, the board will start rotating, right? If I have a hang over here, right? So this force is also responsible to make this board rotate, and as away I go, my torque will be more, right? Because if this is my axis with respect to that, right? And as close I push this, the torque will be lesser, right? So let's go back to the topic and understand what is torque on a dipole, which is placed in uniform electric field. But before talking about torque, let's talk about force. What is force on this system of dipole, right? So you know, force is given by what? What is the relation between force and field? It is Q into E. So if I need to calculate force on a charge, I just need to multiply it with electric field, right? So these two charges are of opposite nature, right? So force on this plus q charge will be what? Q into in the opposite up direction, right? Force on this negative charge will be Q into in the downward direction, right? You're able to follow this one. It is force on this plus Q is QE in the upwards direction, away from the field. Force on this minus Q is q in the downwards direction towards the source of field, right? So if I talk about the net force, you can see that it is plus QE on the top, minus QE on the bottom. So net force is what? QE minus QE, which is 0, right? So net force is 0. So hence this system is in equilibrium in terms of force, but this has a torque acting on it, which is responsible to, which can make this system rotate. How? Let's say how. Okay. So before going to that, what is torque? Torque is cross product of distance and force, right? And this is my axis. This is actually my axis, right? So these two distances are A and A. So what exactly is the dipole moment of this dipole? It is P equal to Q into 2A. This is the dipole moment, right? Now, with respect to this axis, there are two forces acting. One is QE and one is QE in the downward direction, right? So as I said, torque is cross product of distance and force, right? So distance from this axis to this point is A, right? The force is QE, right? So let's say tau 1, okay? So the distance is A, the force is QE, and if I resolve this cross product, it will become sine theta, right? Sine theta. But what is the direction of this torque, right? So to calculate the cross product, you have a simple rule. Take your hands along R and curl it around F, and it will give you the direction, right? So this is my direction of R, right? This is R, and this is the force. So if I take along R and curl it towards F, that it is going out of the board, right? So let's say the out of the board is, let's say, Z axis, right? So it is X, Y, and Z, right? So let's say this is K cap. K cap is the unity vector around the Z axis. So I'm considered out of board is Z, inside the board will be minus K vector, which is minus Z, right? So this is tau 1. Let's talk about tau 2. So tau 2 is also at a distance A. It has a force QE only, but if I curl it, so again this is my distance of R, curl it towards F, again it is out of the board, right? So it is again A QE sine theta K cap, right? So now you can see that both torque direction are in out of the board, which is along the Z axis, right? So net torque will be what? Tau 1 plus tau 2, right? Which is A Q K Q E sine theta 2 times, right? And if I write in terms of this P, which was PE sine theta, right? Which is P cross E. So the torque on a dipole placed in a uniform electric field is given by P cross E, right? So what if this theta is 0? What happens? Theta is 0 means this dipole is aligned with the axis, right? So if theta is 0, my torque on this dipole is 0, right? So the tendency of this dipole will be to move back perpendicular to this parallel to this electric field, so that it will not experience any torque, and hence it will get an equilibrium. What if theta is 90, which is exactly perpendicular to this axis and the direction of electric field? Then the torque will be PE, which is the maximum value of torque possible, and in that state this dipole will experience maximum torque, right? Okay. Right. So we just studied torque on a dipole when it is placed in uniform electric field, which is given by the cross product of P and E, right? So what about the potential energy, right? So whenever there is a force associated with a system, there is a work associated with the system, and hence there is a energy associated with the system. The force is capable of doing work, and work done means energy consumed, right? So again, let me draw that simple diagram of field showing a dipole here, minus Q plus Q, having angle theta with field, right? So we know that a torque on this dipole is given by P cross E, right? Which is PE sine theta, right? So let's say if I need to rotate this dipole, right? Rotate this dipole, that too against this field, right? I need to do a work, because this field this torque is created because of the electric field over here, which is rotating dipole in a proper direction. But if I need to rotate it, I need to apply certain amount of work. I need to do certain amount of work, which would need certain amount of energy, right? So what is work done? Work done is given as what? Work done, work is what? Force into displacement in terms of translation motion. But what about rotation? In rotation, when torque comes into picture, the work is given by, I'm talking about the small work, which involves small theta also, if I need to rotate it by small theta. So what exactly work is? Pe sine theta d theta, right? And if I am doing it against this torque, so it will become minus of, right? Exactly. So this is what is work done to rotate this dipole at through an angle d theta against this particular effect of field, right? So if I talk about change in potential energy, right? So you already know, you might have studied. Change in potential energy is given by negation of work, which is what? Pe sine theta d theta, right? So net potential energy of this dipole, if I need to calculate, I need to have a reference, right? That at this particular point, potential energy is 0. At this particular point, the potential energy is what I need to calculate, right? So to calculate the net potential energy, I need to integrate it, right? Integrate this, right? So let's say this is u1, this is u2, okay? And let's say my starting point is 90, right? Just for a reference, and I'm moving to a new angle called theta, right? So what will be the integration of this? Pe cos theta minus sine will come, because integration of sine theta is minus cos theta. This is 90 theta, right? So this is nothing but minus Pe cos theta, right? So this is change in potential energy, which is given by minus Pe cos theta, right? So in terms of dot product, if I write, this is nothing but minus P dot E, right? So this is the potential energy of dipole when placed in uniform electric field. The negative sign obviously indicates that the energy, this energy is corresponding to counter the effect of field and the torque which field is producing, right? Right. So we just finished the concept of dipole, the torque on dipole, and the potential energy in dipole when placed in a uniform electric field, right? Now whatever charges we considered, whatever system we consider as of now, till now, were the discrete system. What exactly is discrete system? So you have a point charge minus q plus q. You would have seen me putting this minus q plus q plus q minus q. So you see that these systems are discrete. Like you have a point charge placed at distinct distances, and they are not aiding each other, right? They are separate charges, right? Now we will talk about continuous charge systems, right? Continuous charge systems, right? So what exactly is continuous charge system? So continuous charge system are those systems in which charge is uniformly distributed. It might be along its length, it might be along its area, and it might be along its volume. So let's talk about this board, right? Let's say this is a charged board, right? And this has just an area. So you would see that if I pick a small area from anywhere, if I pick a small area from anywhere in this board, I will get a certain amount of charge. But per unit area, that charge will be constant, right? No. Let's take a linear system, right? Let's say this is a wire, right? And this has charge along its length, right? So this charge will be uniformly distributed along the length, right? It's not that here I'll have more charge, here I'll have less charge, nothing like that. If this is a charged body, a conductor, the charge will be uniformly distributed along its length, right? So if I cut a small length from any part of this particular system, or let's say this wire, I'm considering this as wire, so the charge per unit length will be constant, right? So now we have three terms in continuous charge system, right? So one is linear charge density, right? Linear charge density. Then we have surface charge density, right? Then we have volume, charge, density, right? So you would have come across this term density multiply, right? We would have seen that density is nothing but mass per unit volume or things like that. But here again, this density is also ratio, but this is in terms of charge, right? So linear charge density are for the systems where charges are distributed along the length. Like I just gave an example of a system wire, a rod, or systems like that. So for that types of system, this linear charge density, which is represented by lambda, this is given by charge by length, charge per unit length, right? Okay. Surface charge density, right? So let's say the systems are something like a disk, right? Or system are like sheets, right? So in those kind of systems, the charges will be distributed along its area, right? So in for those kind of system, the concerned charge density will be surface charge density, which is represented by sigma, and this sigma is given by charge by area, right? Volume charge density. Let's say we have 3D systems like a sphere, like this is a duster. Let's assume that this is a conductor for some time. So this has a 3D system, which is a cuboidal shape, right? So for these kind of systems, the charge density will be volume charge density, right? So this is given by rho, and rho is charge by volume, right? Charge per unit volume, right? In term for small charge, a small length, this is dq by dl. Let's say this is what dq by dA, and this is dq by dV, right? And unit you can easily say this is what unit is coulomb per meter square, coulomb per meter cube. And this is, since it is a ratio of two scalars, these all are scalar quantity. As you can easily say, there is nothing called direction here, right? So for continuous charge systems, we need to know how the charge is distributed in them before approaching for any problem with respect to that, right? Now let's get back to a bit in history. In previous class we talked about a law called, no, we talked about a concept called electric flux, right? Electric flux is nothing but it indicates the number of field lines crossing through the surface area, right? So it depends on two parameters, as I said. One is the electric field intensity, which is given by E, and another one is the surface area. How big is the surface area? How small is the surface area? So let's say we have a point charge, right? This is a point charge plus Q, and let's say it is placed in a some kind of spherical system, right? Spherical system, right? So flux, let's say I cut a small area from this sphere, right? So net area is S, let's say the radius of this sphere is R, so net total area will be what, 4 pi r square, and I cut a small area ds, right, which is area of my interest. Ds is this area ds, and I need to calculate the field at this ds, right, or the flux at the ds, right? So now let's say due to this Q is responsible to supply field lines or for the electric field at this ds, right? So net flux is given by what? The flux is given by the symbol phi. So net flux through this ds will be what? E into ds, right? Sorry. Net flux phi is given by E into ds, right? Since it is a small area, let's say d phi, right? So this will be given by E into ds, right? So electric field at this particular point, this is on the surface, so is given by what, for because of this q is kq by r square, right? This is very clear. Electric field will be given by what, kq by r square, right? And then this is ds, right? So now if I need to calculate for the whole system, right, for the whole sphere, what is the flux due to this q through the whole sphere? So I need to integrate it. So integration d phi will be what, integration k cube by r square ds, right? So integrate, so k cube by r square is obviously constant. Integration of ds will be what? Integration of whole surface is net s, right? Which I just said is 4 pi r square. K cube by r square into 4 pi r square, right? Which is k cube 4 pi, right? And k is nothing but 1 by 4 pi epsilon naught into q into 4 pi. This is nothing but q by epsilon naught, right? Clear? So flux due to this point charge for this surface, spherical surface, is given by charge by epsilon naught, right? Which is charge by permittivity, right? So now this is the basis of a law called Gauss law. Gauss law, right? Gauss law basically says that net flux through any closed surface is given by 1 by epsilon times the charge enclosed by that surface, right? Net flux in any closed surface is given by 1 by epsilon naught times the charge enclosed, right? Okay. So for any closed surface, the net flux will be given by charge enclosed by epsilon naught. Okay. So this is the statement of Gauss law. So that surface is called as a Gaussian surface. For this point charge, the Gaussian surface was a sphere. Why? Because the sphere was symmetrical to that particular point charge, and hence the law was easy to calculate. But Gauss law is independent of the surface size and shape, and it is no dependent on that. And q in is the charge enclosed in that surface, right? So let's say this is a surface and this has plus q, and this is again plus q is outside. So this q is not of interest if I need to calculate flux through this surface. So net charge is what? 2q, right? And again, if I make this plus q as minus q, my net charge will be 0 and flux will be 0, right? You can say that why flux will be 0, because there is one plus q, another is minus q. So number of field lines which will be outgoing and number of field lines which will be incoming, they both will be same, right? Okay. Right. So we just understood the term of Gauss law, which basically says that the net flux through any closed surface, which is Gaussian surface, is 1 by epsilon naught times the charge enclosed by that surface, right? So we have a topic here called flux of uniform field through a cylinder, right? Let's say we have a cylinder, right? This is a cylinder. This is a cylindrical surface, right? And we have an electric field E in this direction, right? So now we need to calculate the flux, net flux through this uniform cylindrical surface, right? And there is nothing is given that there is any charge inside this or something like that. So if you go by definition also, flux basically means the net number of field lines crossing a unit area. So for this surface, if I talk, so number of incoming lines and number of outgoing lines will be same. So net flux, you can say that it will be 0. But if we go by the formula and things, so this has three surfaces, right? Let's say this is S1, this is S2, and this is S3. So S1 and S2 are the plane surfaces, S3 is a curved surface, right? So if I draw area vector, this will be in this direction for S1 outwards, S2 it will be in the opposite direction, right? And S3 will be perpendicular to it, right? Right. Okay. Right. So for S3, you can see that the area vector is perpendicular to the direction of field, right? What is flux? Flux is dot product of area and electric field, right? Electric field density. So it is Es cos theta. So for 3, phi on S3, it will be obviously 0 because theta is 90 degree, right? Let's talk about S1 and S2. So flux due to S1 will be what? Es cos 0, right? Let's say this area is S, and flux due to S2 will be what? Es cos 180, right? So now net flux is phi s3 plus phi s2 plus phi s1. You can say that if I add these two, it will become what? Cos 0 is 1, cos 180 is minus 1. So this will add to 0. So net flux is through this cylindrical surface is 0, right? So Gauss law is independent of any size of Gaussian surface which I draw, right? Let's say for a point charge, right? For a point charge, I said that this is a Gaussian surface, and we can calculate electric field at any point or things like that. Why we choose this surface is it is a symmetrical surface, and for us calculations will be easier, integration will be easier. We need, because since we need know the simple laws of integration, for us it will be easier. Even if I talk about a charge which has charge distributed along the line, you can say that perfect Gaussian surface for this will be a cylinder, right? This is again a symmetrical, right? So in tomorrow's topic, we will talk about applications of Gauss law on how can we calculate electric field intensity because of different system of charges, continuous charges, and using Gauss law, right? So, so Gauss law is nothing new. It is a derivation from Coulomb's law, right? Like we just derived Gauss law using Coulomb's law. So Gauss law is nothing but the extension of Coulomb's law. First, Gauss law only takes into account the charges which are enclosed by the surface, right? It will not take into account the charges which are outside, right? And the net charge, you already know the charge follows additivity. So if there are multiple charges in a system, you need to take all charges into account to apply Gauss law, right? So yeah, we will stop here for today, and then tomorrow we will discuss the applications of Gauss law and solve more problems on Gauss law.